5, 4, 3, 2, 1, 0.
Assalamualaikum warahmatullahi wabarakatuh, and hello everyone, welcome to our video presentation of Group 3. In this video, we would like to explain about the Chapter 3 with the title, The Relational Database Model. But before we jump into the material, let me introduce my group. I'm Nuraini Ilham as a moderator, and my friend Rizka Almerenda Husni and Nirwan. Without further ado, let's jump into the first material, which is relational model. What is the relational model means? The relational model, introduced by E.F. Code in 1970, is grounded in predicate logic and set theory. The predicate logic is used extensively in mathematics to provide a framework in which an assertion, which is statement of fact, can be verified as either true or false, while set theory is a part of mathematical science that deals with sets or groups of things and is used as the basis for data manipulation in the relational model. Building on these foundations, the relational model is defined by three major components, which is the first one is a logical data structure represented by relations, which organize data in a structured format. The second one is a set of integrity rules, which ensures data consistency and accuracy over time. And the last one is a set of operations, which governs how data can be acquired and manipulated. Now we move to the second material, which is a logical view of data. Earlier hierarchical and network models often created complex and inefficient database structures. The relational model solved this problem by focusing on the logical representation of data and its relationship instead of physical storage details. This makes it easier to design and use databases, similar to how an automatic transmission simplifies driving. The relational databases use tables, which are two-dimensional structures of rows and columns. A table is also called a relation as defined by E.F. Code. Each table represents a group of related entities, also known as an entity set. There is a characteristic of relational table. The first one is a table is perceived as a two-dimensional structure composed of rows and columns. The second is each table row or tuple represents a single entity occurrence within the entity set. The third is each table column represents an attribute and each column has a distinct name. The fourth is each intersection of a row and column represents a single data value. The next is all values in a column must conform to the same data format. The sixth is each column has a specific range of values known as the attribute domain. The seventh is the order of the rows and column is immaterial to the DBMS. And the last one is each table must have an attribute or combination of attributes that uniquely identifies each row. To better understand the characteristic of tables, let's look at the following illustrations. First, we see that the table is made up of rows and columns. Each row represents a single entity, in this case, one student. Each column represents an attribute, such as student number, last name, or GPA. At the intersection of a row and a column, we have a single data value, like a specific student's GPA or date of birth. Column values follow a consistent format. For example, the DOB column only stores dates. Each column also has an attribute domain, which means it only accepts values within a defined range, such as GPA values between 0.0 and 4.0. Finally, every table must have a unique identifier. Now we move to the next material, which is keys. Keys are important because they are used to ensure that each row in a table is uniquely identifiable. Keys are also used to establish relationships among tables and to ensure the integrity of the data. A key consists of one or more attributes that determine other attributes. For example, invoice number will determine invoice date and customer name. So there is a most important part of the key, which is a primary key. So the primary key is ensure unique identity for every row. For example, in the student table before, there is a stu_num is primary key that uniquely identifies each student. Now we move to the right parts of this slide, which is dependencies. A key's role is based on determination. Knowing one attribute lets you determine another. Similar to the revenue minus cost equal profit. We know the two gives us the third. In databases, based on relationships among attributes, not the formulas. In dependencies, there is the functional dependencies, which is one attribute or determinant determines another or dependent. And there is a full functional dependence too, which is all attributes in the determinant are essentials. On this slide, we can see the different types of key used in relational databases. The first one is a superkey. Is any attribute or combination of attributes that uniquely identifies each row in a table. Next, a candidate key is a minimal superkey, meaning it has no unnecessary attributes. From the candidate keys, we usually choose one to be the primary keys, which ununiquely identifies each records and cannot contain null values. Then we have the foreign key, which is an attribute in one table that links to the primary key of another table, helping maintain relationship between tables. And the last one is a secondary key. It's used mainly for data retrieval purposes, not for uniqueness. Move to the integrity rules, which ensures data consistency in relational databases. The first one, you have the entity integrity. This rule states that all primary key entries must be unique and cannot be null. The purpose is to make sure every row has a unique identity, and sovereign keys can properly reference primary key values. For example, invoices must have a unique number and cannot be null. This way, each invoice can be identified correctly. The next part is referential integrity. This rule applies to foreign keys. A foreign key may be null, but if it has a value, it must match an existing primary key value in another table. The purpose is to prevent invalid or orphaned records. For example, a customer may not have an assigned sales representative which is valid, but if a representative number is given, it must exist in the related table. These integrity rules are crucial because they maintain the accuracy, reliability, and proper relationships of data in the databases.
Okay. For the next explanations, I will explain about the relational algebra. But first of all, please introduce. My name is Nirwan. And yeah, we'll explain about relational algebra. So the data is relational tables is limited value unless they are or the data can be manipulated to generate useful information. And these sections, I will describe the basic data manipulation capabilities of the relational model. So relational algebra is defined as a set of mathematical principles that form of basis for manipulating relational table contents. So there are 8 main functions. So the first one is select, project, join, intersect, union, difference, product, and divide. Okay, and for formal definition and terminology. So the relational model is based on mathematical principle, and the manipulation of data is a database can actually be described in mathematical terms. And the good news is that as database professionals, we do not need to write mathematical formulas directly. Instead of we work with data using SQL as a powerful language that hides the underlying math. And still, understanding the mathematical foundations can give us a clearly idea of like what kinds of operations can be performed, and it also helps us write queries more efficiently and effectively. And one important thing is the key advantage of using formula mathematical is representation is that they are unambiguous. So like what we know is that mathematical statements are very specific, and which means that database designer can also need to precise in the language they use. So for this reason, while it is common to use the word relation and table interchangeably, in formal definition, the term relations is preferred because it is mathematically accurate. And an important concept here, like yeah, is the distinction between a relation and a relation variable, often shortened to relvar. And a relation refers to the actual data that we see in a table. A relvar, on the other hand, is a variable or a container that holds the data. So for example, if you create a variable named qt way to hold integer values, the variable itself is not an integer. It implies stores integers. In the same way, like our table structure is a relvar, while the actual data is stored inside it is the relation. So a relvar itself has two parts: the heading and the body. The heading contains the names of the attributes, while the body contains the relation or the actual data. To make this distinction easier in formulas, we usually use lowercase letter for relation, and uppercase letters for relvar. Lastly, the relation algebra can provide us with a set of mathematical principles for manipulating table contents. And as what we said in previous, there are 8 main operations. There are select, project, join, intersect, union, difference, and product and divide. These operations they are precise to and ambitious, and they are making them powerful tools for working with a relational database. Okay, and then next is a relation set operator. So the relational operators have that property of like a closure, that is the use of relational algebra operation on an existing relation or a tables produce new relation. And numerous operations have been defined. Some operators are fundamental, while others are convenient but can be derived using the fundamental operators. So in this section, the focus will be on the 8 operators that I have mentioned before. There is select or restrict, project, union, intersect, difference, product, join, and divided operations. So yeah, I will explain them one by one. The first one operators is select or restrict. So select, also known as restrict, refers to as an array operator because it's only used one table as input. It yields value for all rows found in the table that satisfy a given condition. So select can be used to list all of the rows, or it can yield only rows that match a specific criterion. In other words, it's like a select yields a horizontal subset of a table, and select would no limit the attribute return, so all attribute of the table will be included in the result. And the second one is the project. Project yields all value for selected attributes. So for definitions of project itself is project is in relational algebra, an operator used to select subset of columns. So accepting only one table's input, and project will return only the attributes requested in the order in which they are requested. In other words, so project yields vertical subset of a table. So the first one is select is horizontal subset, and while the project is a vertical subset of table. So project will not limit the rows return. So all rows of the specified attributes will be included in the result. Yeah, and the third one is union. So yeah, union is a relational algebra, an operator used to merge or append two tables into a new table, so dropping them duplicate rows. The table must be union compatible. So unions is combine all rows from two tables, excluding duplicate rows. So to be used in the union, the tables must have same attribute, characteristic, and or we can say in the other words that columns and domains must be compatible. And when two or more tables share the same number of columns, and when they are corresponding columns share the same or compatible domains, they are said to be union compatible. And the definitions of union compatible itself is two or more tables that have the same number of columns and the corresponding columns and have compatible domain. And the fourth one is intersect. Intersect in relational algebra, an operator used to yield only the rows that are common to two union compatible tables. So intersect yields only the rows that appear in both tables. As what the definition of intersect itself, as with union, the tables must be union compatible to yield valid result. For example, you can use intersect if one of the attributes is numeric and what is character based. So for the rows to be considered the same in both tables and appear in the result of the intersect, the entire rows can must to be exact duplicate. And the fifth one is difference. Difference yields all rows in one table that are not found in the other table. That is, it subtract one table from the other. As with union, the tables must be union compatible to yield valid result. And the definition of difference itself is in relational algebra, an operator used to yield all rows from one table that are not found in another union compatible tables. The effect of difference operation is the figure the figure that is on the slide. However, that we can note that subtracting the first table from the second table is not the same as subtracting the second table from the first table. Okay, the next one is product. So product in relational algebra, an operator used to yield all possible pairs of rows from two tables, and the product is of one table has for example, if one table have 6 rows and the other table have 3 rows, the product yields all is composed of 6 multiplied by 3 and the result is 18 rows. So the effect of a product operation is shown that figure on the slide, what you see. The product is denoted by the multiplication symbol x, and the product of the customer and agent relation would be written as follows. So customer multiplied agent. A certain product produces a set of sequence in which every member of one set is paired with every member of another set. In terms of relation, this means that every tuple in one relation is paired with every in the second relation. Okay, for the next one is join. Join in relational algebra is a type of operator used to yield rows from two tables based on criteria. And there are many types of join, such as natural join, data join, equi-join, and outer join. So join itself allows information to be intelligently combined from two or more tables. Join is the real power behind the relational database, allowing the use of independent tables linked by common attributes. Okay, and the last one is divide. Divide in relational algebra an operator that answers queries about one set of data being associated with all values of data in another set of data. So the divide operator is used to answer questions about one set of that data being associated with all values of data in another set data. The divide operation uses one double column table as the dividend and one single column. For example, in the figure in the screen, it shows that a list of customer and the product purchased. And the table first on the left, table 2 in the center contains a set of products that are of interest to the users. A divide operation can be used to determine which customer, if any, purchase every product shown in table 2. In the figure, the dividend contains the P code and choose code columns. The diffuser contains the P code columns. The table must have a common column. In this case, the P code columns. The output of divide operation on the right is a single column that contains all values from the second column of the dividend or the table of choose code. They are associated with every row in the diffuser. This section I will explain about the data dictionary and the system catalog. So the data dictionary definitions itself is a database management component that stores metadata. It's about data. The data dictionary contains the data definition as well as their characteristic and relationship. The data dictionary may also include data that are external to the database management, also known as information research dictionary. The thing that we have to note is the data dictionary is an example of human view of the entities, attributes, and relationship. The purpose of this data dictionary is to ensure that all members of database design and implementation teams is the same table and attribute names and characteristics. The database management internally stored data dictionary contains additional information about relationship types, entity referential integrity, checks and enforcement, and index types of component. This additional information is generated during the database implementation storage. And the data dictionary itself is sometimes described as the database designer's database because it records the design decision about tables and their structure. Like the data dictionary, the system catalog contains metadata. And the system catalog can be described as a detailed system data dictionary that describes all objects in a database. Including data about table names, a table creator and creation data, number of columns in each table, data types corresponding to each column, index file names, index creator, authorized users, and access privilege.
Okay, so now we get into the relationship within the relational database, which are classified as one-to-many, one-to-one, and many-to-many. The one-to-many relationship is the standard in the relational databases. It occurs when one entity is related to many others, but each related entity is connected to only one parent. For example, one painter can create many paintings, and one curse can generate many classes, but each paintings or class belongs to only one painter or course. This relationship is implemented by placing the primary key of the one side as foreign key in the many side. While in a one-to-one relationship, one entity is related to only one other entity. For example, one professor can chair only one department and one department can have only one chair. While sometimes necessary, such as in generalization hierarchies, one-to-one relationships are uncommon and may indicate that the entities could be merged into a single table. Technically, a one-to-one is treated as a restricted form of one-to-many, where the many side is limited to one occurrence. While the last but not least, the many-to-many relationship means many entities in one set are associated with many entities in another, like students and classes. Since it cannot be implemented directly in a relational database, it is resolved by creating a composite or bridge or associative entity, such as an enroll table linking student and class. This table includes foreign keys from both entities and may also hold attributes like grades. By converting many-to-many into two one-to-many relationships, redundancy and anomalies are reduced while maintaining referential integrity. Next, we're going to be talking about data redundancy revisited. So, data redundancy can cause anomalies that harm database effectiveness, but relational databases control it through the use of foreign keys. While foreign keys cannot completely remove redundancies, they minimize errors and support data integrity. Sometimes redundancy is necessary, such as in data warehousing or when preserving historical accuracy. For example, copying product prices into invoice lines ensures past sales reports remain correct even if current prices change. Planned redundancies like these are part of good database design. Additionally, some of the redundancies, such as automatically generated line numbers in invoices, are acceptable since they aid usability without creating anomalies. The next one coming is indexes. An index is an order arrangement of keys and pointers used to quickly locate rows in a table, similar to how a library catalog or books index helps find information efficiently. It consists of an index key and pointers that identify the location of data. Indexes speed up data retrieval, allow data to be retrieved in a specific order, and can be based on one or multiple attributes or a composite index. They are also crucial for implementing primary keys as the DBMS automatically creates a unique index for them. While a table can have many indexes, each index is linked to only one table and SQL commands can easily create them. Okay, now let me walk you through Code's rules for relational databases. Code's rules explain what makes a database truly relational. First, all information must be stored as table values, and every value must be accessible by table name, primary key, and column. Nulls should be handled consistently, and even metadata like schema must be stored in tables. The system should support one complete language for defining, manipulating, and managing data. When it comes to operations, any updatable view must be updatable through system, and the database must support set-level inserts, updates, and deletes. Applications should not be affected by changes in the physical storage or by changes in table structure like adding or reordering columns. Integrity constraints must be stored in the database, not in applications. Finally, users should not notice whether data is local or distributed, and low-level access must never bypass integrity rules. Rule 0 reminds us that database is relational only if it uses its relational features exclusively. Altogether, these rules ensure databases are consistent, reliable, and adaptable to change.
That's all from us. Thank you for watching. And if you have any question, don't forget to put it in the sekolah. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.